In this module, we're going to start focusing on oxidation numbers. Now, oxidation numbers are a concept that we use to describe the number of electrons that are transferred during a reaction. This comes back hard and heavy in Chem 2 when we look at electrochemistry. But right now, we need you introduced to the concept so you can start recognizing oxidation reduction reactions, or what we call redox reactions, where electrons have been transferred within the system. And we need you to be able to start recognizing it for titration data as well. So you should be able to identify and predict the products of oxidation reduction reactions that can happen from single displacement or double displacement reactions. You should be able to assign oxidation states. It happens in other reactions too, but those are the easiest ones to see. Assign oxidation states to elements and compounds, identify a redox reaction, oxidizing agent, and reducing agent. So what is an oxidation state or an oxidation number? Chemists have assigned a number to each element in a reaction called an oxidation state. This is what's allowing us to determine the electron flow within the redox reaction. Again, redox itself stands for reduction, oxidation, what we call oxidation, reduction reactions. Oxidation states are not ion charges. They often match. So don't get that confused in your head. When I say iron has a +2 oxidation state, that means it also has a +2 charge. That's coincidental. Oxidation states are imaginary charges based on a set of established rules that we have developed to be able to describe the transfer of electrons within a reaction. Ion charges are real, measurable charges. So what is oxidation? What is reduction? Oxidation is the loss of electrons. A species has lost electrons. It's still the same species, it's just lost electrons. Remember, when it loses electrons, losing electrons, if it's from a neutral species, that's when you're going to form a cation. If it was a negative species, if it's an anion to begin with, it could go back to being a neutral species. Lost electrons, not protons. Throughout Gen Chem, we talk about electrons moving, not protons. Reduction is the gaining of electrons. So gain electrons. If it was a neutral species, it can become an anion. If it was a cation that gained electrons, it can become back to a neutral species. So again, no protons moved. The two ways you can remember which is which, the two mnemonics I can offer, is Leo the lion goes grr and oil rig. Pick which one makes the most sense to your brain. Leo the lion goes grr, loss of electrons is oxidation. So Leo, loss of electrons is oxidation. And grr, gain of electrons, is reduction. Or oil rig, oxidation is loss of electrons, reduction is gain of electrons. An oxidizing agent is a substance that oxidizes another species. The substance itself is reduced. This throws students off. Think about a real estate agent. They are not selling real estate to themselves, they're selling it to you. So an oxidizing agent oxidizes something else. It does it by being reduced. It's able to oxidize a different species by accepting electrons and being reduced itself. A reducing agent is a substance that reduces another species by being oxidized itself. It loses its own electrons to give them away to someone else. Oxidizing agents steal electrons from an unsuspecting element. Oxidizing agents and reducing agents are reactants. They are not products. They are always going to be reactants. So how do we figure out the oxidation numbers? Well, we have a set of rules that we use to determine the oxidation number of a specific species. The easiest way to approach oxidation reduction reactions is by focusing on the oxidation state of each element. Rule number 1, the oxidation number of an element in its neutral elemental form is 0. So its most neutral form of the element, if it's sitting there, it is a 0. Cl2, its oxidation number is 0. Why is it Cl2? It's a diatomic. Its most stable state is at Cl2, so its oxidation state is 0. O2, also 0. Excuse me. Oxygen is a diatomic, so its most stable state is O2, and its oxidation state would be 0. Fe is iron. Iron is a metal. Metals as a solid, except for mercury, is its most stable state, so it will have an oxidation state of 0. Carbon graphite, 0. If I had S8, 0. P4, 0. They are the most stable states. Aluminum, just aluminum metal, 0. The oxidation number of a monatomic ion is the same as its charge. So if I have just, Zn2 plus, its oxidation state is +2. If I have nickel 2 plus, its oxidation state is +2. Looking here, Al2O3. Split this apart. Think about how you used to do your naming and split these back apart. Al2O3 means 2 aluminums and 3 oxygens. The oxidation state on aluminum is +3. I'm not going to say +6. I'm going to say +3 because it's for each element. There is 2 aluminums, but each aluminum has a +3 state. Oxygen, -2. Oxygen really likes to be -2. It's its favorite state to be. Oxygen wants to be 0 or -2. It doesn't always get its way, but it almost always gets its way. FeO. We know the iron here has to be +2 because we know the oxygen wants to be -2. So the oxygen, -2, the iron, +2. Fe2O3, we know we have 2 irons. They're going to be 3 plus each because we have 3 oxygens that are each going to be -2. Oxygen, -2, the iron here, +3. So aluminum, oxygen, iron, oxygen, iron, oxygen. Notice oxygen's getting its way. It almost always does. A few exceptions, and I'll show you those. But iron, again, it's going to be +2 or +3, depending on its oxidation state. Na2S, sodium sulfide. Sodium can only be a +1 charge. Sulfur wants to be a -2 charge. So sulfur here will be a -2, while each sodium is +1. Excuse me. Notice I do not say +2 for the sodium. I say sodium has a +1 charge. In binary compounds, the element with the greater electronegativity is assigned a negative oxidation number equal to its charge in the simple ionic compounds of the element. You haven't learned electronegativity yet. That comes later. But electronegativity is how much it can hold electron density towards itself. Generally speaking, the element listed second is more electronegative. So the element listed second in the formula is going to get the negative charge. The sum of the oxidation states equals the overall charge. So let's look at these examples. If I have H2O, oxygen is listed second. Oxygen really wants to be a -2 charge. I'm going to let oxygen be a -2 charge, which is going to let the hydrogen here be +1. Now, some students still have a hard time seeing that. You can do this algebraically as well. The compound itself has a neutral charge to it. I know that there are 2 hydrogens plus 1 oxygen. I'm going to use X for oxygen, giving me overall 0 charge. But I know that the oxygen wants to be a -2 charge. So 2H minus 2 has to be equal to 0. Solve this algebraically. This means 2H has to equal 2, and each H has to be equal to +1. My hydrogen here has to be +1. My oxygen has to be -2. Oxygen is more electronegative. It's listed second. It's going to get the negative charge. One exception to that is hydrogen peroxide, because again, what this is doing is describing how many electrons a species has gained or lost. hydrogen cannot lose more than one electron. It just doesn't have them. A hydrogen atom has one electron. If I follow the same logic we've been following for H2O2, each oxygen would have a -2 charge, so each hydrogen would have to have a +2 charge. But again, that's not possible. So hydrogen peroxide is one of the exceptions. We know that hydrogen cannot go greater than a +1 charge. So I have 2 +1s plus X for oxygen, giving me a neutral species. 2 plus X equals 0. Or sorry, 2 plus, there's 2 oxygens there, I apologize. So I've got 2 hydrogens, each represented by a +1 charge, because that's all it can lose is 1 electron. 2 oxygens, and overall the species equals 0. 2 times +1 is 2, plus 2x, giving me 0. 2x is -2, x is equal to -1. My oxygen here has to be a -1 charge. 2 oxygens at -1, 2 hydrogens at a +1, give me an overall neutral charge. Another example that I've written on the board here, or on the slide here, is OF2. Fluorine is actually more electronegative than oxygen. When we learn about electronegativity, we find that fluorine is the most electronegative element there is. Oxygen is number 2, meaning fluorine is going to get its way. The fluorine is going to be the most negative, getting the negative charge, giving oxygen the positive charge. Fluorine is a halogen, so fluorine really wants to be a -1 charge. I have oxygen plus 2 -1 charges, overall equaling 0. X minus 2 equals 0 because 2 times -1. X equals +2. My oxygen here has to be a +2 charge. Oxygen's not thrilled about it, but it can do it. Because again, these are made up construction of numbers to describe electron flow. If I look at PCl3, I know chloride is the more electronegative element. It's listed second. It wants a negative charge, and chloride is a halogen, and halogens like to have that -1 charge. So I have phosphorus plus 3 -1 charges has to equal 0. Phosphorus minus 3 has to equal 0. Phosphorus must be equal to +3. Same logic to apply to PCl5. Phosphorus plus 5 times a -1 equals 0, because again, chlorine is going to get its way, -1 charge. Phosphorus minus 5 equals 0. Phosphorus must be a +5 charge. So notice, depending on what the phosphorus is in, it could be a +3 or a +5 charge. And I will zoom this out in a minute so we can see everything nicely again too. It's just easier to write on the board or write on the screen this way. The last 2 examples we have are nitrate and nitrite. I have a -1 charge here. I have to pay attention to that. The sum of the oxidation states has to equal that overall charge. I have nitrogen and oxygen. Oxygen's more electronegative. It's listed second. Oxygen wants to be -2, and it's going to get its way. So nitrogen plus 3 oxygens, each at a -2 charge, has to equal a -1 charge overall because the ion itself has a -1 charge. Nitrogen minus 6 equals -1. Excuse me. Nitrogen has to be a +5 charge. If I look at it in nitrite, nitrite is N3 minus, that would just be N3 minus oxidation state nitrite. Got 1 nitrogen. Again, my oxygens are going to win and be -2 here. A nitrogen plus 2 oxygens, each at a -2 charge, giving me an overall -1. Nitrogen minus 4 has to equal -1. Therefore, the nitrogen itself must be a +3 charge. Notice I am writing +3 and minuses, like I'm writing them very intentionally that way. That just got really small. Hydrogen plus 1, oxygen minus 2. Hydrogen plus 1, oxygen minus 1. Oxygen plus 2, fluorine minus 1. Phosphorus plus 3, chlorine minus 1. Phosphorus plus 5, chlorine minus 1. Nitrogen plus 5, oxygen minus 2. Nitrogen plus 3, oxygen minus 2. For generalizations about all of this, that will help you determine the right states. First, metals can only have a positive oxidation state or zero. Why? Because metals are not going to gain electrons to make negative states, I mean. Metals only gain electrons if they are in a higher oxidation state. Mainly meeting metals do not want to form anions. Nonmetals can have both positive and negative oxidation states or zero. They can go any direction. The highest oxidation state an element can have is equal to the number of valence electrons it has. It does say here the old group number, it's equal to number of valence electrons. So the old group numbers are, when you look at the table, you got your alkaline metals, your alkaline earth, you got your transition metals, you got your P block over here. And then, below that, you've got your lanthanides and actinides. So the way that the table's numbered now is 1, 2, 3 to 12, 13, 14, 15, 16, 17, and 18. The old group numbering used to be 1, 2, skip the transition metals, 3, 4, 5, 6, 7, 8. So when I say old group numbers, the highest oxidation state element can have is the old group number. I mean these numbers that are written here. So it's kind of like groups 1 and 2 stay the same, but for these groups here, it's kind of taking their numbers and subtracting it from 10. That's the highest oxidation state it can have, meaning the most positive. So like alkali metals, can be 0 or plus 1. Alkaline earth, really like to be 0 and plus 2. Noble gases can go from 0, or from 8 down to 0. Halogens can go from 7 down to -1. Chalcogens, or oxygens family, can go from 6 down to -2. Just for the nonmetals, by the way, don't forget you got a stair step happening somewhere in here. I'm not drawing this very well, but the stair step is in here, and there's metals underneath here. So nitrogen's family can go from 5 down to 3, carbon 4 to 4, -3, 4 to -4. The lowest oxidation state element can have is the old group number -8. So that's why I see like halogens are in the old group number 7, current group number 17, but they can go down to a -1 state, or oxygen down to a -2 state. So what is the highest oxidation state that chlorine can have? Chlorine is a halogen. Currently group (17), which is old group number 7, means that the highest it can have, the most positive, is an oxidation number of 7. What is the lowest? Lowest meaning 0 or negative. Chlorine is a nonmetal, so it can go negative. So it's going to be that old group number -8, or a value of -1. Highest meaning most positive Magnesium can have. Magnesium is an alkaline earth metal. It can be positive 2. It can lose up to 2 electrons. The lowest, it is a metal. So the lowest it can go to is 0. It will not go negative. Metals don't want to be anions. Redox reactions. So reactions where oxidation reduction occur are called redox reactions or oxidation reduction reactions because oxidation cannot occur without reduction. Basically, when a species is oxidized, it loses electrons. Those electrons have to go somewhere. Conservation of mass. The first law of thermodynamics tells me it can't create nor destroy things. So if electrons are lost from one species, they have to go to another. They go to a different species and reduce that other species. One species cannot be oxidized without another substance being reduced. The easiest way to approach redox reactions is to determine the oxidation state or oxidation number of every element in a reaction. So previously I said oxidation is losing electrons, which is correct. A more useful definition of oxidation is an increase in oxidation number or state. Previously I said reduction is gaining electrons, which is correct, but a more useful definition is a decrease in the oxidation number or state. Decreasing meaning going closer to 0. Or negative. If you're thinking about like a number line. An oxidizing agent is a substance that is reduced and oxidizes something else. And a reducing agent is your substance that's oxidizing, it's reducing something else. In order to be an oxidizing agent, a substance must contain an element in one of its higher oxidation states. Again, to be an oxidizing agent, it has to be reduced itself. Higher oxidation states meaning it has to be able to accept electrons. In order to be a reducing agent, a substance must contain one of an element in one of its lower oxidation states, because in order to be a reducing agent, it has to be oxidized itself. It has to be able to lose electrons. And then what differentiates the common definitions of oxidation and reduction used in general chemistry versus organic chemistry? If you're not going on to organic, you're not going to deal with this, but if you do, you're going to see this happen. So let's just go ahead and define the difference. Fundamentally, oxidation reduction is the same thing, but we look at it from a different perspective. So, oxidation versus reduction. In Gen Chem, we say oxidation is a decrease in number of electrons or an increase in your oxidation number. Reduction is an increase in the number of electrons or a decrease in the oxidation number. Now, this is always true. This is the fundamental definition of oxidation reduction. In organic, though, they are going to say that oxidation is an increase in oxygen content, a decrease in hydrogen content. Reduction is a decrease in oxygen content, an increase in hydrogen content. It's not wrong. They're just not focusing on the electrons. So you will see that difference when you get to organic, and I just want you to understand they are saying the same thing. We're just saying it from a different perspective. Determine the oxidation number of each element in this reaction and answer the following questions. Magnesium solid, that's in its most elemental form, most stable form, will have an oxidation state of 0. HCl, hydrogen can only gain or lose 1 electron. It's in a compound, so it's going to be a plus charge, because the chloride is going to think the negative charge should be -1. I know chloride is going to win the negative over the hydrogen. Magnesium chloride. Chloride will be -1. There's 2 of them, so magnesium must be +2. Plus magnesium is an alkaline earth metal, it wants to be +2. In H2 gas, it's its most stable form, it's going to be 0. Now I'm going to look and see what changed. Magnesium went from 0 to +2. That means it lost 2 electrons. Loss of electrons is oxidation. So magnesium has been oxidized. Notice I'm writing magnesium here, not magnesium ion. Magnesium ion was not oxidized. It is the reactant side. The magnesium solid has been oxidized. Because it has oxidized, it has reduced something else. It is a reducing agent. If I look at the chloride -1 to -1, nothing changed. I look at the hydrogen and I see the hydrogen went from +1 to 0. But notice that wasn't really hydrogen on the reactant side, that's really H+. Magnesium went from 0 to +2, specifically Mg2+. Hydrogen went from H+ to H0, which was really just H2 gas, having no oxidation state. So which element is reduced? Hydrogen. Hydrogen gained 1 electron. Each hydrogen atom gained 1 electron. Overall, magnesium gave up 2. 2 separate hydrogens each gained an electron to be able to form H2. So this is my oxidizing agent. It allowed magnesium to be oxidized, taking its electrons to be reduced itself. Oxidizing agent H+, not H, not H2, the reactant side. Find the oxidation numbers of each element in the following compounds. CO2. I've got carbon, and I know I've got 2 oxygens, and I know oxygen likes to be a -2 charge. The compound overall has a 0 charge to it. So carbon -4 is equal to 0. Carbon must be +4. And if you can just see that in your head, you don't have to do all the math like that. I don't care. Just some students have a hard time seeing it. My lead plus my 2 oxygens at -2 have to be a 0 charge. So Pb -4 equals 0. Pb has to be equal to +4. So this must be lead 4 oxide. My chlorate, ClO3-, my Cl, plus 3 oxygens, each at a -2 charge, have to equal -1, because I have a negative charge on this polyatomic. Cl -6 equals -1. Cl must be equal to 5. And H2O2 is back. We see that one again. Again, oxygen likes to be -2, but it can't. Hydrogen cannot go greater than +1. It literally doesn't have any more than 1 electron. So I've got 2 times +1 plus 2 oxygen, giving me a 0 charge. 2 plus 2x equals 0. 2x equals -2. X equals -1, and I'm using X to represent oxygen because writing an O and a 0 look the same on the paper. Determine the oxidizing agent, reducing agent, each reaction below. So let's look at this one first. Copper 2 chloride reacts with aluminum to form copper and aluminum chloride. The chloride I know is going to be the -1 charge. There's 2 of them, which means copper has to be a +2 charge. Aluminum in its most stable state is 0. Copper is 0. Chloride, -1, making this aluminum +3. Notice here, this is a single replacement reaction. When I swap partners, my copper doesn't pair up with anything here. My chloride does, because the aluminum is going to act as a cation in an ionic form. I'm not going to pair up my copper and my aluminum. That's not going to happen because they both act as cations. just like I wouldn't pair up two anions. So be careful with that. I've got my copper going from +2 to 0, meaning it gained 2 electrons. It's been reduced. Therefore, it's the oxidizing agent. So oxidizing agent is my copper 2+. Copper 2+ was reduced. My chloride remained unchanged, but my aluminum went from 0 to +3. It lost 3 electrons. It was oxidized. It is the reducing agent. It was able to reduce the copper. And that is aluminum, not aluminum 3+, aluminum. Let's look at this next reaction. Fe2O3 plus 3CO, giving me Fe and 3 moles of CO2. Oxygen is a -2. There's 3 of them overall, so -6. And this iron must be +3 because there's 2 irons overall. CO, oxygen likes to be -2, so copper must be +2. Iron, 0. Oxygen likes to be -2. There's overall 2 of them, so -4 charge. So copper must be +4. My iron went from +3 to 0. It gained electrons. My carbon went from +2 to +4. It lost electrons. My oxidizing agent, Fe3+. My reducing agent was my carbon. Gained electrons, so it was reduced. Lost electrons, it was oxidized. And this last one looks kind of like a beast. H+, +1, it's by itself. Let's see. Mn, +2, it's by itself. Those are the easy ones. MnO4-. There's a minus charge here. Mn plus 4 oxygens at -2 each have to be a -1 charge. Mn minus 8 has to be a -1 charge. Mn must be a +7 charge. And you don't have to write that out, I don't care. I'm just doing that for students who can't see it as well. C2O42-. I've got 2 carbons plus 4 oxygens at -2 charge each, -2 overall, 2 carbons, -8 equals -2. My 2 carbons have to be equal to a +6, so each carbon is +3, each oxygen is -2. H2O, oxygen is -2. Each hydrogen has to be +1. In CO2, each oxygen is -2, so the carbon must be +4. So let's see what changed. Hydrogen, +1 to +1, no change. Manganese, +7 to +2. That gained some electrons. It was reduced. It's an oxidizing agent. Oxygen, -2 to -2, -2, -2, nothing has changed there. And my copper went +3 to +4, lost electrons, being oxidized, therefore reducing agent. So, on this last example, I apologize, 1 second. My pen is not working. Oxidizing agent is the magnesium 7 plus. Reducing agent is the carbon. So manganese 7 plus, that is a 7. And the reducing agent is carbon. Practice your oxidation states. Get these down because they matter when we start doing redox titrations. You need to be able to understand where these species are coming from.